So, the important non-dimensional number called Damkohler number, okay. So, that is defined now as a ratio of chemical time Tc and the physical resistance time Tr. So, Damkohler number this is very important number which is defined Tc by Tr. So, based upon the Damkohler number we can say the category of the control of the combustion phenomena. Okay, now when Tc, the chemical time is much higher than the flow resistance time Tr, then the combustion phenomena is kinetically controlled. Okay. So, what happens here? Reactants are thoroughly mixed, very well mixed reactants. For example, this is the chamber. This is a chamber in which I am having some reactants. So, fuel, oxidizer, and on the completion of the reaction products will be formed, and it has some temperature. So, temperature initially will be, when the reactants are present in this chamber, it will be T, U, okay, and when the products are formed it will be Tf. So, let us say this is the scenario, but at every time instant everything is well mixed here. So, thoroughly mixed, this is x equal to 0 to x equal to L, there is no gradient, okay, that is a well mixed or uniformly distributed reactants are present. Now, after completion of combustion, products will be uniformly present in this. Okay. So, the gradients of species and temperature are negligible, 0. So, in this case, when the reactants are present and you ignite it, okay, the depletion or the reactant consumption will depend only on the chemical kinetics based upon the temperature. This is totally controlled by the kinetics, the phenomena of combustion here. Here the Damkohler number is very large. Okay. So, because you can see Tc by Tr, Tr is very small, okay, tends to 0. So, Damkohler number tends to infinity. So, Damkohler number is very large. So, this is the regime where Tc, Tr is very low, Tc is very high. It will take some finite time for the reaction to complete. Okay. So, that is the phenomena which is kinetically controlled. So, for analyzing this, for example, it may be ignition, small volume I take, there is a well mixed reactant, I try to put some energy to ignite it. So, from the initial temperature it goes to a higher temperature. So, that ignition process is kinetically controlled. Okay. So, that is the first category in which you will understand that there is no other gradient. So, I am actually having no gradient in the fuel, oxidizer or temperature and so on. Only the kinetics is going to help us solving this problem. So, how much time it will take for temperature to rise from the initial value to the final value, that will be only dependent on the chemical kinetics, analysis based on chemical kinetics. So, that is the first category in which the transport processes are not at all present. The residence time is very negligible. Okay. Finite rate of kinetics is required, that means it will take some time to reaction to complete. Okay. So, that is what the first category is. The second category, Tc chemical time is much lesser than the Tr, the residence time. Okay. Then the combustion phenomena is transport controlled. Okay. Now, so this is the figure. Fuel is supplied from one side and oxidizer is supplied from another side. You can see that fuel is higher here when where it is supplied, similarly oxidizer is higher here where it is supplied. Slowly fuel is consumed, oxidizer is consumed. When they are consumed completely, you get the flame zone. So, this is the flame zone actually. Okay. So, this is the non-premixed, the other extreme category. In the previous category, everything was very well mixed, the fuel and oxidizer, and uniform temperature it was not. But here you can see that the fuel can have a different temperature and oxygen can have a different temperature. They can come and mix, and once they mix, instantaneously chemical reaction will take place. That is the meaning of this. So, when they diffuse and mix at a particular point at stoichiometric proportion, they just react. they react very, very fast. Like this flame here present here has a chemical time which is negligible. The reaction rate of the reactants are much higher than when compared to the time it requires to transport these reactants towards the flame. So, you can see the gradient of the fuel, a strong gradient of fuel oxidizer is present. Similarly, temperature which is reaching maximum at the flame zone can have a gradient towards these streams here like this. Similarly, products which are formed at the flame zone will diffuse towards the fuel side, towards the oxidizer side and so on. So, clearly you can see that there are gradients as opposed to a zero gradient scenario for the kinetically controlled combustion. Here chemical time is negligible as and when the fuel here, fuel and oxidizer are meeting at a stoichiometric proportion, instantaneously they react. So, this is also called infinite rate chemistry. The infinite rate kinetics. The chemical kinetics is so fast that it can be assumed to be occurring at an infinitely faster rate. The reaction is going to finish within some negligible time, but the fuel and oxidizer transported towards that point will take more time. So, that is going to control the phenomena. That is the second phenomena. Here reactants are mixed only at the flame zone, they are not premixed. The gradients of the species are significant as indicated here. The rate of depletion of the reactant mixture is dictated by the relatively slower transport rate of reactants towards the flame zone. Chemical kinetics is much faster. Damp-Coulomb number tends to 0. The previous case that was very large, Damp-Coulomb number was very large, here Damp-Coulomb number this goes 0. The third category is the category where the both terms are of same order, Tc, chemical time, residence time are of same order, then you cannot neglect anything, both are important, okay, that is the third phenomena. So, here Tc is much greater than Tr, Damp-Coulomb number is very large and fully kinetically controlled, one extreme. Second extreme is Tc is much lesser than Tr, you can see the gradients, chemical kinetics is very fast, the transport is going to control the, when I say infinite fast chemistry, I do not need kinetics at all to analyze this flame. To analyze this flame, I do not need to worry about the kinetics, you do not need to worry about single step, multi-step, elementary, global, no reactions, nothing is required. Only the rate at which the fuel and oxidizer are going to be fed here, that will dictate the formation of flame. So, for example, if we take this scenario, if I now increase the fuel flow rate, the flame will shift to the right, okay, or if I increase the oxygen flow rate, the flame will shift to the left, correct. So, that is the way we see this. Why when I increase the fuel flow rate, the fuel requires more oxygen, the oxygen is fed at the same rate. So, the fuel will now go towards oxygen side, the flame will shift towards that. So, that means that by controlling the flow rates, I can locate the flame anywhere I want. See, if the momentum of these two jets are kept constant, then I can see that this flame can be at center, correct. So, I can adjust my flame location based upon the control of flow rates, that is the transport controlled. I do not need to worry about the kinetics, kinetics is very fast, already whenever they mix they will react. So, that is the tendency of the chemical kinetics there, okay. So, that is second extreme. The third is you have to care for both, where you have Damp-Coulomb number approaching 1, you have to care for both, okay. So, the flame you have to incorporate some kinetics to analyze the problem, and again you have to resolve the flow process also properly. So, both have to be done in this third category. First category, I do not really worry about the flow process, flow or any diffusion, anything, I only worry about the kinetics here. The second, I do not worry about kinetics at all, I only worry about the flow, how to properly resolve the flow. The third, I have to worry about both. I have to take care of both. Okay. Now, we have seen the Coulomb equations, which are actually pretty complicated equations. You can see that for example, for reactive flows, the set of species conservation, what we are going to get. Though those species conservation equations, if there are n species, capital N species, we will have we have to solve n minus 1 partial differential equations. Okay, and these equations will have a non-linear source term. So that means that it's really complicated to solve this when you have a non-linear source term which is exponentially dependent on temperature. A slight increase or decrease in temperature will affect the source term and affect the solution of this. We have to solve it numerically, and this numerical solution will suffer when there is update. So we have to really worry about importing changes at a smaller level and merge the solution, especially if it is time dependent and so on. Okay. On the other hand, again, if you see the energy equation, you have fluxes due to diffusion of species, enthalpy. Similarly, you have the source term, omega dot triple dash into Hi. So these terms are non-linear terms, okay, the non-linear source terms which we have. So what happens here, again the solution is complicated. So is there any way we can simplify this? See the category 2 here, and to some level to category 3, we can try to minimize the chemical kinetics. So mainly due to the chemical kinetics, the non-linear terms are arriving. So if you have scenario where diffusion or transport phenomena or processes are going to control the flames, then we can go for what is called simplified chemically reacting system, which was introduced by Professor Spalding. Okay, simple or simplified chemical reacting system, SCRS. The assumptions made in this system is, okay, so we have major products, minor products, etc. So all we have seen the elementary reactions with lot of radicals like O, H, HO, H2O, etc., HO2, lot of things are there. So major products are CO2 and H2O. So the concentrations of the minor species OH, OH and this HO2, etc., are very less. So we will not worry about the minor species, we will only consider the major species. Second is, chemical reactions are going to be very, very fast. Transport processes are very, very slow. So in that case, I do not need to worry about multi-step reactions, I go for only a single step reaction, and this is given like this: 1 kg of fuel plus S kgs of oxidizer producing 1 plus X kg of products. This is the reaction I consider. So these are the assumptions made, and Spalding defined a quantity called conserved scalar. Yes, see, for example, mass fractions is a scalar, correct, but it has a non-linear source term. For example, when you conserve yi, you have a non-linear source term omega I triple dash, non-linear source term. So this is kg per meter cube second. Okay, so that source term arrives, but if you have a scalar which is called conserved scalar, then there will be no source term in the conservation equation. How will you define such variable? That is what is we have to see. So my main intention of this simple chemical reaction system is to eliminate the source terms, because I do not want chemical kinetics. The interaction of chemical kinetics is very minimum here or negligible here. So how can we eliminate the chemical kinetics and concentrate on the transfer processes? That is what we are trying to see here. So taking the same global reaction, 1 kg of fuel, S kg of oxidizer. So I am saying fuel is F, oxidizer is OX, and product is PR. Okay, I am not taking into account of products like H2O, CO2, etc. Just group everything and call it product stream, PR. Now let us consider for simplicity one dimensional coordinate, say x coordinate, and we also consider steady problem, transient term. Okay, dou by dou t is neglected. So one dimension, dou by dou t is neglected, I get ordinary differential equation rather than the partial differential equation. So, when I write the conservation for fuel, what I get is convective term. So, x direction, velocity is u. So, u is the x direction velocity and rho is the mixture density. I am considering mass fraction of the fuel. So, dyf by dx, there is no transient term. If I put a transient term, then yf will be a function of x and t. So, the ordinary differential equation will be converted into a partial differential equation. I will add this term. Okay. So, now this is not there, steady problem. So, I write a ordinary equation here. So, this plus I am just considering ordinary diffusion. Please understand, I do not consider this any complicated diffusion, Soret effect, etc. here. So, ordinary diffusion, I have a diffusion coefficient. So, this is the diffusion term. So, convection of the species, this is diffusion of the species and the source term. Source term has not been eliminated so far. So, this source term remains. So, that means obviously the scalar yf is not conserved scalar. Okay, it has a nonlinear source term. Okay. So, this is the way I write the convective term, the diffusion term, source term. Okay, right. Same thing for the oxidizer, rho u into dyox by dx equal to diffusion term d by dx of rho d dyox by dx plus the rate at which the oxidizer is consumed. Okay. Then products, rho u into dypr by dx equal to d by dx of rho d dypr by dx plus the rate at which products are formed. So, these three equations you can see that there are nonlinear source terms. Okay, one more assumption what I make, I know u. So, or if I want to solve for u, I have to again solve for continuity equation, the mass conservation of the mixture plus the momentum equation together. If I solve, then I will get the u. So, let us assume that u is known to us now. Okay, or it is not a problem to solve u also. Okay, by solving the momentum equation along with continuity, I can solve for u. Okay, and then one dimension it is simplified. Now, please understand that as I told before, I am considering only the ordinary diffusion. Solar diffusion is also neglected, that is fine for us. Then one more assumption what I have made here is the diffusion coefficient d are taken as the same for all this, for fuel, oxidizer or products, the diffusion coefficient d is same. That is what the third thing I am using here. So, I am simplifying, already I am simplifying. As I told you, I need not calculate this. When we discuss about the thermophysical properties here, we already told that I can say d is equal for all species. Two assumptions which commonly are made are this Lewis numbers etc. are equal to 1. So, that I will also take the d, the diffusion coefficient for a particular species going into the mixture to be same for all the species. Similarly, I can also invoke this specific heat is same for all the species. Okay. These are the simplifying assumptions I invoke, because if you see for a mixture there is no much big change. Okay. Again, it may be a dependent on temperature or not, that is second question. Again, if it is not dependent on temperature, then we have to calculate this at a particular temperature called average temperature, that we will come to that later part. But what I am assuming here is, instead of using individual values for d of a particular species going into mixture, I am assuming that the d is same for all the species. That is one of the important assumption. So, with that assumption here you see that the diffusion coefficients are taken as the same. So, that will give you this. So, rho d here is same for all the species f, ox and pr. So, this is the one dimensional. Still we have not eliminated the non-linear terms. Again, solving this is again not easy because of the non-linearity in the source term. You can see this will depend on say a exponent of minus Ea by RUT into concentration of say f and concentration of O to the power m and n. So, this will be the equation here. So, you can see the exponential dependence on this temperature here. So, any small variation in temperature will cause a huge difference in this value. So, that may make the numerical scheme to oscillate, some instability can occur. So, how to avoid this? So, that means that we have to very carefully proceed with the solution of this equation when there is a exponential dependence on temperature for the source terms. So, elimination, and we do not require this, that is the main criteria here for diffusion controlled or transport controlled flames. We can eliminate this. So, how we will do this, that is the question. So, now we will say that U is known to me, or by solving the continuity and moment equation we can you take U. We will not worry about U much. Now, energy conservation. Again I am writing this without the pressure viscous dissipation work terms. Radiation is also neglected, due for as usual neglected, and one dimensional. Transient term is neglected. So, one dimensional only. So, the ordinary derivative is written here, rho Cp x dash velocity dt by dx equal to the conduction term d by dx into thermal conductivity into dt by dx. Okay. Then again you can see the non-linear term are there, omega I triple dash into hi summed over all the species, and you can see the diffusional flux of each species due to the temperature gradient here. Rho yi into ui diff is the diffusion flux into the enthalpy. So, that diffusion to the surfaces. So, now here I invoke Lewis number equal to 1. I already shown that these non-dimensional numbers can be same. So, when you say Lewis number equal to 1, alpha by d equal to 1. Okay. What is alpha? Alpha equal to lambda by rho Cp. So, that will be equal to d. So, that means lambda by Cp equal to rho into d. So, that is what I have written here. So, this is actually lambda. So, lambda by Cp equal to rho d. So, thermal conductivity. So, K or lambda represent thermal conductivity. So, thermal conductivity by Cp will be equal to rho d. I am also taking the second assumption, all the Cp's, same values for all the species. Cp's of all the species is same. That also I am invoking here. So, all the diffusion coefficient of all the species is same. Similarly, all the Cp's of each species is same. So, by invoking this, okay, I can simplify this equation further. Now, what else I am doing here? When I say Cpi is just Cp, Cpi of all the species are same, this is only Cp. Now, what happens? Then this Cp dt by dx will be constant, that can be taken out, and then by what I have is only rho I ui diff, that will be the diffusion flux. So, diffusion flux summed over multiplied by Cp into dt by dx, that will cancel out, this term will go out. Then the source term, this term, when I write hi Cp into T plus HFI. Okay. So, now if I say Cp into T, and when I sum it over all this, so this can be written in this term. HFI only will come into play, because Cp into T into omega I, we can write this term. So, when I substitute here, you will write omega dot sigma of this into Cpt. So, this will be equal to 0. When I add the source term of all the species, some will be produced, some will be destroyed. So, that the net rate of production will be equal to net rate of consumption. So, omega dot triple dash sigma over all the species will be equal to 0. So, this term will be written only in terms of heat of formation. So, omega dot triple dash in HFA, still this source is there. So, now you can see this, that is the source term, which is non-linear in nature. Okay. Again you can see, so this particular term can be further expanded. The last term of the above equation is expanded now further to show that it is equal to the product of net reaction rate of fuel and the heat of combustion.